Derby branch of the Royal Aeronautical Society is proud to host NASA Programme Manager Roger Hunter to start our autumn lecture series. This is our first virtual lecture for our branch. Roger Hunter, in his current capacity, leads the NASA Ames Centre's Small Spacecraft Mission and Technology Development Programmes, as well as the NASA Ames Small Spacecraft Integrated Project Team. He also is a technical lead for the Defence Advanced Research Project Agency's Phoenix programme. Previously, he served almost 6 years as the project manager for the Kepler mission, NASA's first mission capable of finding Earth-sized planets around other stars in the Milky Way galaxy. Prior to joining NASA in 2008, Roger led the Boeing Global Positioning Systems Center in Colorado Springs, Colorado. He served 22 years in the US Air Force. Colonel Hunter's assignments included Commander, 2nd Space Operations Squadron, Deputy Operations Group Commander for the 50th Space Wing, and Program Manager for the XSS-10 Microsatellite Technology Demonstration for Air Force Research Laboratory. He also had assignments with HQ US Air Force Space Command and HQ US Air Force at the Pentagon. Hope you enjoy.
Thank you for the introduction, and it is a pleasure to be with you again today. I was at headquarters for Rolls-Royce 4 years ago in the Derby branch, and my lecture at the time was mostly about the Kepler mission. And Kepler Space Telescope, as described in the introduction, had a sole purpose, and that was to do a statistical survey of the Milky Way galaxy with the intent of determining just how many Earth-sized habitable zone planets or habitable worlds are in the population of the planets that are in our galaxy. And when I spoke with you in 2016, the mission was still moving along, but we have now decommissioned the spacecraft in November of 2018. And I want to do a quick look back on the Kepler mission before I cover 2 other topics, including the small spacecraft technology development program that I'm involved in now, and then just give you a glimpse into some other upcoming NASA missions. So first, let's talk about Kepler. How did it work? This animation is a reminder of the presentation from 4 years ago, and it's a simple concept. Kepler is a photometer. It's not an imager like Hubble, but it's a photometer, and it measures the brightness of stars precisely so that when the planet is crossing the face of the star, as you see in this animation, it dims the star slightly, and we can measure that dimming to such a precision that we can determine the size of the planet, its orbital period, and also its distance from the star. And we did this on hundreds of thousands of stars. The primary field of view when Kepler launched was looking through the Cygnus constellation, and you can see that checkerboard square up there, which represents Kepler's field of view. And that's where we looked for the first 4 years in trying to determine just how many planets are out there, what are the shapes and sizes, what are the planetary systems look like when compared to our solar system, and moreover, how many Earth-sized planets are in the galaxy. This is just a quick reminder that I presented just from a few years ago for those of you who attended. This is the Kepler field of view, and the 3 yellow dots you see represent the known exoplanets, exoplanets being those planets beyond our solar system that had already been detected by other means. And this is the fertile ground that we were looking at when we started hunting planets with Kepler for the first 4 years, looking through the Cygnus constellation. And after 4 years, this is what we found, just in that particular area, over 4,700 planet candidates. Many of these have been confirmed and are on the way to just about every one of them being confirmed. Of course, we colorized these to represent the different sizes of planets. And of course, the pale blue dots, thank you, Carl Sagan, represent those that are Earth-sized planets in that field of view. Now, we, of course, as we near the end of the mission and as we decommissioned the spacecraft, we started looking back on the statistical analysis. What have we found? But as we were looking back in the 3rd and 4th year of this mission, we suffered some anomalies. And so those of you who will move on to be engaged in the aerospace industry, or you work for European Space Agency or NASA, you always end up with anomalies. The first 4 years, we were able to point Kepler at the original field of view, and you can see it on the left-hand side of this graph. And you can see the checkerboard pattern. But in the third year, and then in the fourth year, we lost 2 gyroscopes. We call them reaction wheels sequentially. And we need 3 to point accurately, and we were left with 2 reaction wheels after the first 2 failed. So we came up with an ingenious way of still recovering the spacecraft and recasting it as what we called Kepler K2. We could not point at the original field of view, but we could still point around in different parts of the galaxy. And you can see the checkerboard patterns in other parts, and we were able to still find planets, even though we were not able to continue for the entire 9.5 years of the mission to look at the original field of view. The first 4 were at that block you see on the left, and the remaining part of the 9.5 mission, you were looking at the regular checkerboard squares, but we still found plenty of planets, which added to our statistical analysis. If you go into NASA's archive, you can actually pull this chart up, and it's on the Exoplanet Archive, which is hosted by our Jet Propulsion Laboratory. The numbers I want to point out, it's highlighted in bold there. Once again, it's over 4,700 total candidates and confirmed planets. 4,700. And this was an astounding number to us. And it is also reaffirming that, one, our solar system isn't that unique. There are many other planetary systems out there that are similar to ours, but there's many that are also different from ours. But the number I want to point to you on this chart is one that says candidates and confirmed in the habitable zone, because that's what we were looking for. That was the rabbit that we wanted to pull out of the hat. And so there was 361 that we detected in the entire mission that were either candidates or they were confirmed, and we're well on our way to confirming more of those. In the K2 mission, this is the recast mission after we had lost 2 reaction wheels. We continued to find planets even though we were not pointing in the original field of view, and we found hundreds more there as well. And so we know that there are planets wherever we looked within the galaxy, and we just happened to be looking at different places every time we pointed, but every place we pointed, we were finding planets. This is a summary count. This is what we found, including everything that was detected by Kepler, everything detected by Kepler when it was recast as K2, and there was a follow-on mission called TESS, which is still looking for planets today, and it was based upon the success of Kepler, and it's still operational, and it's actually into its extended mission, and it's still finding thousands of planets as well. But these are just some of the summary charts that have been provided by the mission scientists who've been doing analysis on the mission. But what we want to get to was answering this question that you see on this chart. How rare is the Earth? And what fraction of stars in our galaxy harbor potentially habitable Earth-sized planets? And I know there's some gobbledygook looking equations here, but these were excised from one briefing that was presented just a couple of years ago. But there's another paper that has just recently been submitted to the Astronomical Society, and it provides further affirmation of what we're seeing on this chart. But let me translate what this means for you. We now know that if you go outside, look up in the sky, get away from the city lights, and you start counting the stars, 50% of the stars has an Earth-sized planet in a habitable zone. Our conservative estimate when I spoke with you 4 years ago at Rolls-Royce headquarters in Derby was about 1/5 or 20% of the stars had an Earth-sized planet in a habitable zone. But as we continued the mission with Kepler, and as we decommissioned it in November 2018, and we added also in the results from TESS, the follow-on space telescope, which is also looking for exoplanets, we are now able to assert that half of the stars in the Milky Way galaxy have Earth-sized planets in the habitable zone. That paper is going to be released in the near future, but that is the information that I want to impart with you today as a revisit to the Kepler mission. And if you want to use a foot stopper, and if you want to convey this to any of your family or friends or relatives out there, these are the 2 foot stoppers that we've gotten out of the Kepler mission. Earth-sized habitable planets are relatively common, and planets far outnumber the stars. If there are, for argument's sake, 200 billion stars in the Milky Way galaxy, there are about 100 billion Earth-sized habitable zone planets out there. And if there's a couple hundred billion stars in the Milky Way galaxy, there's hundreds of billions more planets than there are the stars. And so those are the fundamental lessons and findings that we received from the Kepler mission. And there's two I wanted to highlight for you. Now, these aren't real images. These are artist concepts that are based upon some discussions that the mission scientists and the principal investigators had with an artist when we're trying to convey what we've been finding. And this depiction you see here is a planet that was detected in 2015 called Kepler K218b. So that means it was discovered when Kepler was in its second recast mission after we had lost 2 reaction wheels. But we're able to still point and still find planets. And this one we found interesting, and what's being represented here is a 2-planet system. And Kepler K218b is the large bluish one. We don't know what the planet actually looks like. This is just the artist's concept that's in the foreground. But when we detected this planet in 2015, we also did a follow-up on it with the Hubble Space Telescope and with Spitzer. And what was interesting about this particular discovery, and this is the only one so far, using Hubble and using Spitzer and their combined analysis, we found water vapor in the atmosphere of this planet through spectroscopy. This is the only exoplanet so far in which we have determined that there is water vapor around another planet that is not in our solar system. This is about 124 light years away from us in the Kepler K218 system. This was an astonishing find. The next one is what some people call Earth's cousin. And of course, this is an artist concept as well, but the planet we're talking about is on the left, Kepler K-452-B. And we wanted to point this one out because it's kind of like a super Earth, but the most interesting thing about it is that it orbits a sun-like star. Its orbital period is similar to that of Earth. Of course, we're 365.25 days to make our journey around our sun, and this one is around 389 days. And the stars that they orbit are quite similar to each other. So if we were looking for a cousin or a 2.0 Earth, this is the one that some of the scientists point to, but this one is even farther away than the one I just previously mentioned, Kepler K218b. This one is almost 1,400 light years away from us. So I just wanted to highlight a couple of the findings from Kepler that I think were somewhat remarkable in certain ways. One being similar to the way that Earth orbits our own host sun and similar in size, and the other one has water vapor in its atmosphere. So there's some interesting findings that the Kepler mission with in its original cast mission looking through the Cygnus constellation and its second recovered mission, which it only had 2 reaction wheels looking at different parts of the Milky Way galaxy. We're using machine learning now to help us validate some of the planet candidates that Kepler found. And I saw this published by the University of Warwick, in which they had applied machine learning to sifting through the Kepler data, and they confirmed 50 of the new planets. And this was just released a few months ago, and I thought you would find this interesting because there are going to be scientists plowing through the Kepler data, I think, for years to come, because it is such a treasure trove of photometric data with a collection of several hundred thousands of stars that we have collected on since the spacecraft began its journey in March of 2009 and until it was decommissioned in November of 2018. And this image I want to share with you, and this is an image, but of course it's as best we can do with a photometer because photometers are meant to measure brightness of stars. As Kepler was nearing the end of its life, and we knew that we were going to have to decommission it because it was running out of its propellant that we use to maintain its attitude pointing control, we turned Kepler around and pointed it at the Earth. And this is from a distance of about 93 million miles. And of course, at that distance for a photometer that is as precise and sensitive as Kepler's photometer, the Earth lights up like a giant bolt of light, and you can see the Earth-Moon system there. And this is what the last full-frame image that we took with Kepler. And then we said goodbye to it on November 2018. Now, if you may recall from the lecture I gave 4 years ago, I may have mentioned that the orbit of Kepler, it's in an Earth-trailing heliocentric orbit. It follows us around the sun. As we take 365 days to make our journey around the sun, Kepler takes about 371 days, plus or minus. So that means we're like two runners going around a racetrack. And one day, the Earth will lap Kepler, and we will come within a short distance of it. And I just thought it'd be cute and put some spider webs on it, but we actually know the date, September 25th, 2060, and I'm hoping that some of the young engineers and scientists who are tuned in today will actually go up and get the spacecraft and bring it back and put it in a museum, because it has fundamentally changed our view of astronomy. It affirms that planets are plentiful, and it affirms that there are plenty of planets out there that are Earth-sized and in their habitable zone. So where do we go from here? Even though you saw those gorgeous artist concept images of Kepler K218b and Kepler 452-B, we can't really take images of these planets that we discovered because we don't have the optics that are big enough yet. In fact, if we were to try to image planets in our own stellar neighborhood, say within 35 to 50 light years away, we would need a really large telescope. So we started working on this, and back in 2 years ago, NASA awarded a NASA Innovative and Advanced Concepts grant to a Dr. Dmitry Safransky at Cornell University to look at ways we could actually launch a number of very small spacecraft type parts into orbit and let them self-assemble. And so we've started some of the fundamental research and technology development to allow that. And we would have to build a telescope that is larger than 30 meters to allow us to provide the kind of images that are beautifully drawn for us by those artists when we were representing the Kepler K218b and Kepler 452-B. But this is down the road. It's going to take a lot of engineering to do this type of manufacturing and also do this type of assembly on orbit. Now, I'm going to switch gears with you. I'm going to talk about NASA small spacecraft activities, because if you look back at this chart, there are some fundamental things we're doing in small spacecraft technology development today that may enable this type of aperture or this type of telescope in the future. Today, NASA small spacecraft activities are bent in 3 different areas: developing technologies that will allow the extension of small spacecraft into our science and exploration missions for the future. And the other 2 areas, of course, are the traditional areas that are domains for science and exploration that NASA conducts today, albeit with generally much larger spacecraft. Most of my time is spent in the area on the left in space technology development. We're using small spacecraft today to allow us to do Earth observations. Matter of fact, there's some private companies out there that do this. Planet Labs, for example, well, now known as Planet, has its headquarters in San Francisco, California, and those were 3 engineers who came out of NASA Ames Research Center that began a business using small spacecraft to allow the observation of the Earth 24/7, 365. Their mantra is, if you can't see it, you can't fix it. And today they're selling a lot of their data to agricultural businesses, the large agribusiness companies like Monsanto and Archer Daniels Midland, and they're also selling a lot of their data to the U.S. Department of Defense. But they started with small spacecraft. And so we know today that small spacecraft do have a role in providing good science for Earth observation. But my job in the space technology arena on the left is to enhance the capabilities from a subsystem development perspective to allow us to take small spacecraft beyond low Earth orbit and get them into cislunar and planetary space. So this is what our objectives are within this program. Using small spacecraft to allow us to expand our capability to execute more unique missions, because we think these small spacecraft allow themselves to be developed more rapidly and demonstrate more quickly. We think they also afford us a way to do some of these missions at a lower cost, reduce the time it takes from design and development to operations. It may actually enable new mission architectures. For example, imagine conducting a mission around a science object of interest in which you have a swarm of these small spacecraft as opposed to one large monolithic spacecraft. There's several advantages to that. Means one, you get to do multi-point science data collection against the science object of interest. And because you have a number of them, if one or two fail, you still have not lost the mission. Of course, when I talk about new destinations, I'm talking about getting these small spacecraft out of low Earth orbit and getting them out there around the cislunar space, around asteroids, around moons of other planets. And we don't necessarily see them as acting alone. We're looking at some architectures in which we might use them to augment existing assets and future missions in a supporting role. I'm just going to go through a few that are coming up in a near future to show you what we're trying to do with some of these technology demonstrations that are using small spacecraft. And there's two different ones you see here depicted on this chart, and these are about the size of a bread loaf or two bread loaves. The one on the left is called PTD, or Pathfinder Technology Demonstrator, and this is just a 6U spacecraft, 6U being 30 by 20 by 10 centimeters, 1U being 10 by 10 by 10 centimeters. And so we have this demonstrable unit called a 1U, and that's what it means when we say U class. We're talking about a cube shape. Of course, you can see there's a sort of a cubist orientation to the spacecraft. We're going to be testing out with the one on the left different subsystems that will enable us to extend the reach of small spacecraft beyond low Earth orbit, and I listed a few of those across the bottom of this chart, whether it's a water-based propulsion system or a new and a better and improved attitude determination control subsystem, new laser comm, or new types of reflector array antennas, or in the last one you see, number 5, LISA-T, of course we like our acronyms, a new power subsystem, that LISA-T standing for Lightweight Integrated Solar Array and Transceiver, in which we're testing out a new type of solar cell that for these U-class missions provides a dramatic increase in the amount of power, so that when you are deeper in space, you have sufficient power that you can drive the antennas or drive the processors on board so that you can conduct your science exploration mission. Now the one on the right is called CPOD, and this is going to launch next year. And it's going to show two of these spacecraft, and there's two in that depiction, as they're coming closer to each other. They're going to be autonomously docking. We think this is fundamental demonstration that we need to show that we can autonomously dock large parts of a space station or an aperture, a new type of an array on orbit. And if we're able to do this autonomously, we will not need much interference or much direction from the ground, nor will we need an astronaut to assist us in this. So these are two upcoming demonstrations. There's just a handful more that I would like to bring your attention to. We're going to try out some new solar cell technology demonstrators. And the one on the left here is called the Advanced Composites-Based Solar Cell System. This material that's being demonstrated in this one is not the solar cell material itself, it's actually new composite booms, because we discovered that with booms that are trying to fly solar cells in some of our smaller demonstrations previously, that metal booms tend to warp and twist in space. And so we've developed a new composite material that we're going to demonstrate with the solar cell. And actually when this one launched, it's rather large, it's about 81 square meters. At certain lighting conditions, you may be able to see it with the naked eye from Earth. The second one you see is called the Startling Distributed Spacecraft Mission. This is what I alluded to earlier, in which we are considering having swarms of small spacecraft that would be ejected into an orbit around a science object of interest, whether it's another moon or an asteroid or another planet, and would then allow us to provide multi-point science data collection against that science object of interest. We have started moving already into laser comm for our spacecraft. I've already demonstrated with one mission laser comm from two very small spacecraft that are about the size of a tissue box from the spacecraft to the ground. This demonstration that's coming up is going to be demonstrating inter-satellite laser communications between very small spacecraft. And the last one you see on the right is a very short-lived demonstration in which we intend to demonstrate autonomous ranging and topology recovery among 3 1U size spacecraft. But the ones I want to highlight the most for you, this represents our return to the moon in a sense, using small spacecraft, which are going to be used to assist us in either determining the prevalence of water ice formations in the darkest craters of the moon, and with Capstone on the right, proving that there is an orbit between the Earth and Moon that's called a near rectilinear halo orbit, to prove that it's mathematically stable. Now, Lunar Flashlight is supposed to, the one on the left, is supposed to launch late next year on our first Artemis launch. Now, Artemis is the follow-on to the Saturn V rocket. It's going to be on a shakedown run around the moon. It's going to it's going to fly the new Orion spacecraft around the moon and bring it back. But as it nears the moon, it's going to be dropping off a number of these small spacecraft. And the one depicted here, Lunar Flashlight, is about 2 bread loaves in size, a 6U spacecraft, but has a very special laser payload on board, which is going to radiate a number of the craters around the South Pole, and that reflection is going to tell us the prevalence of ice deposits in those areas. Capstone on the right is going to launch in March of next year on its own rocket. We bought a rocket from Rocket Lab, and this is going to be injected into that near rectilinear halo orbit, which is the orbit that we intend to put the new Gateway space station into. But we want to make sure that the orbit is mathematically stable, because no one's ever flown in that orbit before. So we're going to use this Capstone spacecraft, which is about the size of a small microwave oven, as a means of determining the orbit characteristics of that near rectilinear halo orbit. It's going to be ranging between NASA's Deep Space Network on Earth and a spacecraft that's orbiting the moon today called the Lunar Reconnaissance Orbiter. And it's ranging between those two entities. It's going to be relaying the characteristics of that ranging back to NASA, and we'll be able to determine just how stable the orbit is and that it matches its mathematical forecast. So that's been basically a quick overview of the small spacecraft technology program. We've been rather busy with this as we've been developing and improving upon small spacecraft so that they can be used as an important part of NASA's toolbox for the future in conducting in science and exploration missions. This is largely the result of where the technology and electronics revolution has brought us. If you look at your smartphones, for example, you have much more processing capability in your smartphone today than we used when we sent Apollo to the moon back in the 60s. And because of such advancements in those areas of electronics and technology, we're now able to build small spacecraft to allow us to use them as an effective tool for NASA's future science and exploration missions. Now I just want to talk about some upcoming missions that I think you may find of interest. Of course, depicted here are 4 astronauts sitting inside the Crew Dragon capsule. Some of you are aware of Demonstration Mission 1, which launched back in May of this year, which carried astronauts from U.S. soil to the International Space Station for the first time since we retired the shuttle. We had only 2 astronauts on board, and that was considered a shakedown run for the Crew Dragon. But in the mission that's going to launch, I think, middle of next month, we'll be sending 4 astronauts up to the International Space Station on the first operational use of the Crew Dragon capsule. And if you look at this, it makes me think of the movie 2001: A Space Odyssey, because it has that futuristic look to it. And it reminded me of where we were years ago and how small the spacecraft really were. And here's a picture of John Glenn being stuffed into that Mercury capsule called Friendship 7. And you can see from just the size of the door how tiny that thing is. And I've observed also the evolution of cockpits for manned exploration as we went from Apollo 4 to the Space Shuttle and now to Crew Dragon. And so it's really changed a bit over the years. And I'm looking forward to what it's going to be like in the future as mankind extends its reach out further into the solar system. Now, there's been a bit of an interesting conversation as a result of this going on within the Roscosmos, or the Russian space agency, And there's been this taunting that's been going on between two of the cosmonauts and the head of Roscosmos. And one of the Russian cosmonauts tweeted out this picture just a week ago, and he was lamenting what they have to write in for Soyuz and versus what the SpaceX affords its the astronauts that ride up on Crew Dragon. And if you speak Russian, the top of it says, "Needless to say, you can see for yourself." And so it was interesting to watch this sort of spat going on within Roscosmos among the cosmonauts and the head of the Russian Space Agency. This is another depiction of how far we've come in the Soyuz capsule on the left with the cosmonauts crammed into it, and then on the right you can see Elon Musk sitting in one of his Crew Dragon capsules. But there's some other ones that I'd like to make you aware of that are coming up in the near future. Of course, the one on the left is the Boeing Starliner capsule, which is their version of the Crew Dragon. This is scheduled to launch, I think, sometime next year, and this will afford the U.S. another crewed, as in people are on board, capsule for transporting astronauts from Cape Canaveral up to the International Space Station. And the one on the right, NASA partnered with a company called Sierra Nevada Corporation, and it affords us another means of shuttling cargo from the ground up to the International Space Station and returning cargo from the International Space Station. This is a cargo version only. There is not a version of this that is meant to be crewed with any astronauts on board. But I found it interesting because to me it looks like a little sports car version of the space shuttle. And I think this is scheduled to fly sometime next year, and it's a maiden voyage. Now let's talk about the mission that's on its way to Mars. This depiction here is the Perseverance Rover. There is going to be a Wright brothers moment with this particular mission. You see the little helicopter there in the foreground. I'll talk about that in a moment. For the first time, we're actually going to fly an aircraft through the atmosphere of another celestial body. But before we get into that, let's talk about where is Perseverance going after it launched just a couple of months ago. It's scheduled to arrive in Mars in late February, and we're headed for Jezreel Crater. Now, this is a colorized photograph of Jezreel Crater. This is not true color, but I just wanted to highlight a couple of things for you on this photograph and then talk about Jezreel Crater just a bit. That dimple you see there, just to the lower right of the center, that is not the crater. The crater is this huge area that is, you see here in this large blue purplish color, and this crater, we think, was the bottom of a large lake millions of years ago, and that black ellipse you see on the upper left-hand corner, that's where we're aiming to land. Now, there's something interesting about this crater. As you can see on the upper left-hand side, what looks like a canyon that appears to be a place where water flowed into this crater, and on the right-hand side, you can see a place of egress for the water, another place where it would fill in water but flow out. So this is why we're aiming for this, because we think there's lots of evidence of a paleo lake in this crater, and we want to sample this particular crater as the rover makes its way around it. Now, on this chart on the lower left-hand side, you can see Mars, and you see the little gold circle. That's where we're going. That's where we're aiming for. And the larger picture, you can see the ellipse where we're landing, represented by the white hash mark, and the gold colored snake trail, worm trail, is the notional path for Perseverance at this time. There's one other thing that I want to point out that's different about this particular rover than the Curiosity rover, which landed on Mars back in August of 2012. It's a very similar landing technique, but this one is going to be a bit different. It's a little more complicated and a little more elegant in a sense. As it's making its descent onto the Martian surface, there's going to be some quick terrain comparison that's going on for the sky crane. And after the parachute detaches, we're going to do some quick mapping to make sure we don't land on those ridges that were to the left of the crater. And if necessary, the sky crane would do a divert so that it can land within a crater itself. So there's a little bit of improvement in the way that we're landing this particular rover on the surface of Mars as opposed to Curiosity. Let's now look at this helicopter. When the first time I was looking at this, it reminded me a little bit of Cubesats because you can see the body of it here. It's very lightweight because the Martian atmosphere compared to our atmosphere is very thin. It's only about 1% of the density of Earth's atmosphere, and for the most part, it's all carbon dioxide. About 95% of the atmosphere of Mars is carbon dioxide, but it's mostly a very thin atmosphere. So we had to make this helicopter very, very lightweight so that we could provide enough lift when we land. And there's an animation I'd like to share with you. And after the rover has landed and we've done all the normal systems checkouts and everything's operating, we're going to deploy the helicopter from underneath the rover, and the rover is going to back away from the helicopter to some distance. Now this thing is solar powered with some batteries on board, and so we have to let it charge up for a while. Of course, this animation is sped up quite a bit because we don't normally drive rovers even at that speed on the Martian surface. But after it is charged up sufficiently and the batteries are practically at 100% capacity after charging, we will engage the rotors, and we're going to have several flights of the Ingenuity, that's the name of it, the Ingenuity helicopter, across the Martian surface. And there's going to be some simple flights, there'll be some up and down, and this is going to be, this animation here depicts one that's a little more robust, and this is probably towards the end of its demonstration cycle. Now we consider this to be a technology demonstration. It's not necessarily conducting science. We just want to see how well we control a deployable from another rover in the atmosphere of another celestial body. And so this is going to be, as I said earlier, a Wright brothers moment for Mars. And as it's flying, we're going to actually be tracking it with a camera on board the rover. And we're going to provide, maybe not necessarily live, but we'll provide recordings of this after we have conducted these couple of missions on the Martian surface. And it's going to fly around a bit. I think it's going to be, there's a simple camera on board. I think you're going to see an animation here that shows that it's taking pictures, but this is mainly just to do comparison of where we told us to go versus what the terrain is underneath the helicopter. And after it completes its fly around, it will land and charge up again, and we'll do several demonstrations of this. But this is going to be an interesting demonstration, and I hope that this will be another tool that we can put into NASA's science and exploration missions for in the future, when we can have deployables from other rovers when we return to other bodies within the solar system. But this is going to be an interesting mission, and I look forward to this after the Perseverance Rover lands on Mars in early of 2021. There's one other thing I want to point out about this rover that I think is kind of interesting. And underneath the rover, you can see the technicians here installing it. Those test tube looking things are actually going to be used to collect samples across the bottom of Jezreel Crater. And I think there's about 43 of those, and they're all going to be cached somewhere in the crater for retrieval on another mission in the future and then return to Earth. So that is one more interesting aspect of this mission I thought you might find intriguing. There is a interesting mission that is orbiting the asteroid Bennu today, and it's depicted in this image. And it's the spacecraft that's called OSIRIS-REx, and this is about to happen. On October 20th, this spacecraft, which has been orbiting this asteroid for quite some time now, the mission's been ongoing for about 3 years or so, that arm-looking device you see hanging underneath the spacecraft is going to do a touch of the asteroid, and it's going to collect a sample of the asteroid and put it into the conical-looking shape you see on top of the spacecraft and return this to Earth. And this is going to happen in just about a week. and it's going to stay near the asteroid for just a few months to make sure that, one, we've collected enough of a sample, and once we're satisfied that we have collected sufficient sample from the asteroid, the spacecraft will do a turn and burn and return to the Earth, and we'll recover it in late 2023, I think, is the time frame for the return of OSIRIS-REx. So I'll make sure that you're aware of this mission because it's imminent. This is the area that is a close-up photograph of the asteroid where the sample collection is. If you look in the lower center part of this, you see a large boulder. That's about the size of a school bus. And just to the right of that large boulder, you see this dark-looking spot. It's just around that dark-looking spot is where we're going to make the sample collection for OSIRIS-REx of this asteroid called Bennu. A couple of missions I want to make sure you're aware of that are coming up and will hopefully launching late next year. This is the James Webb Space Telescope. It's undergoing its final assembly, integration, and test at a facility in Southern California. This is supposed to launch late next year. This is the follow-on to Hubble. Now, this is not going into the same orbit that Hubble is. This is going out to Lagrange point L2, which is about 1 million miles on the other side of the moon. I'm certainly hoping this works properly because you may recall, those of you who have a history of Hubble, we had to do some repairs and also upgrades on Hubble, and we used the space shuttle to assist us with that. Well, at this time, the space shuttle has been retired, and the space shuttle didn't have the legs on it to also reach out to Lagrange point L2 on the other side of the moon. This artist depiction here is of the Artemis rocket, the follow-on to Saturn V. This is also scheduled to launch late next year, and this is going to provide NASA's heavy lift rocket for future missions, including launching certain parts of the Gateway space station out to that near rectilinear halo orbit that I mentioned earlier. And finally, there's this one. This is referred to as Dragonfly. This will be the second time that we will have flown a helicopter through the atmosphere of another celestial body. This is going to Titan. This launches in the year 2027. Titan is the second largest moon in our solar system, and it's the only moon that has an atmosphere. Now, this is a bit bigger than the Ingenuity drone or helicopter I showed you in the previous animation. This thing weighs about 1,000 kilograms, and it's nuclear powered. You can see the drum-looking device on the back end of this quadcopter. That's where the nuclear power plant is, but it uses batteries to fly or turn the rotors on the quadcopter, and so after the battery is discharged, before it completely discharges, it lands and then it charges up again and conducts another flight. This is launching in the year 2027. It'll take, of course, when you're going out to Titan, which is such a distance, it's going to take a few years to cruise out there. And it'll take about 7 or 8 years to get out to Titan, but then it's going to deploy onto the Titan surface and fly through Titan's atmosphere. And we're looking forward to this mission, even though I may be retired from NASA by then. I'm not sure yet. As long as I'm having fun and enjoying the missions that we're conducting, I probably will want to stick around and see this one too. So I want to I'll end right there. I just want to give you a quick update on where Kepler ended up, and that the results continue to be rewarding from the Kepler mission. We now know that there are many more planets and stars. We know there's many habitable zone Earth-sized planets out there. I wanted to give you a quick snapshot on what NASA's doing with small spacecraft technology that will enable us to use small spacecraft even more so in a number of our science exploration missions for the future, and then just give you a glimpse of some upcoming NASA missions that are going to happen in a not too distant future that I thought you might find interesting. So I think I will end there, and I think I will go back to Paulus and Anima for questions if you have any.
Thank you, Roger. I think we have got a few questions. But again, just a request to participants, please type in your questions. So we'll go through a few questions we've got. The first one, I think it's more a generic question. Will the recording be available? Yes, we intend to share the recording in next few days. It all depends on how good the quality of recording we end up getting from Teams. So we'll have to trial. This is a trial basis for us right now. So we'll see how it goes. Okay, there is a question here. Swarms of small sats with solar arrays visible to the naked eye, a nightmare for astronomers. Any thoughts on how to stop things like this and Starlink causing massive light pollution?
Yeah, it's everybody is aware of Starlink, and I'm sure there's a number of astronomers. His Starlink spacecraft are a bit bigger than my small spacecraft, and the small spacecraft that I intend to supply to NASA through our technology development are not meant to stay in low Earth orbit. We're going out into cislunar space and out beyond, but I am quite aware of the issues that astronomers are raising about the reflectivity of Elon Musk's Starlink satellites. And he's got several hundred of those up there now, and he's planning on launching even more. I heard that he's listened to the astronomers and he is willing to try to do something to reduce that signature. I think there's another issue here that we need to think about as well, besides clouding the astronomers' telescopes. There's another one with traffic management in low Earth orbit. And the Department of Commerce with the US has been tasked with providing, more of doing a better job of being a space traffic manager, because if have all these spacecraft up there and you can see this movement into going beyond Earth observation, because you look at a number of the small spacecraft and larger spacecraft now, they're oriented towards Earth observation, observing what's happening on the surface of the Earth from the perspective of climate change and traffic, surface traffic, whether it's air traffic or ocean going traffic. And now you see this movement by Elon Musk with Starlink to providing space-based internet, and that number of spacecraft that they're planning are far outnumber these other ones that are being used for Earth observation. And so there's a number of policy, I think, changes that should be considered about how that's going to be managed. So the ones that I'm sending up there, we're doing technology demonstrations. We let those things burn back into the atmosphere. But I really appreciate the astronomers' concerned with Starlink, and perhaps when OneWeb kicks off and they start launching thousands of these spacecraft, because I know the astronomers are not going to be happy with that. And I'm hoping that those providers like Elon Musk and the OneWeb guys are going to be cognizant of that and are willing to discuss how they can reduce their signature so that you don't cloud the sky and ruin it for a number of the astronomers who are trying to do their business.
Thank you, Roger. The next question is, does NASA intend to carry Cubesat payloads on all Artemis's launches?
I think there's an intent to try to provide a lot of rideshare opportunity. Even the Department of Defense has been talking to us about providing rideshare, so that because when these big rockets go up, or even the mid-sized rockets go up, they have some extra capacity, because the industry has gotten better about building spacecraft, because of the miniaturization, and they're much more capable now than they were back then when we started going into space. I think there's an intent for NASA to provide more ride shares for Cubesat or small satellites, whether they're going into low Earth orbit or to geosynchronous orbit to cislunar space. Most of the things that I'm working on are trying to extend the reach of these small spacecraft to get into cislunar or planetary space, and NASA is the only one that's actually going there right now, along with the European Space Agency. And of course, China is now developing capability, showing that they can launch to the moon and also go to Mars as well. So I think NASA will continue to try to provide some rideshare opportunities for CubeSats or small satellites on some of its other missions.
Okay, thank you. This one, I think I had a similar question as well. So it is certainly interesting to see that Kepler identified more than 350 planets that may be considered to contain life. What are the key parameters that are used to characterize the life does exist or can exist on that planet? It's $1 million question, I think.
Yeah, it is. It's the question is, what constitutes life? It's because when Bill Barucki, who's the principal investigator for the Kepler mission, He and I've had a number of conversations about this, and of course, when you get a few glasses of wine into some of these scientists, that loosens their lips up and they start talking about all kinds of things. Frank Drake, you may know him, the guy who came up with the Drake equation. He and I were having a discussion about this one time as well, and it boils down to we have this fundamental humanocentric arrogance that life must be like us. So NASA Kepler mission was specifically tuned to go find these Earth-sized planets in a habitable zone because we assume that, well, we have life on this planet, there's probably gonna be life on planets that are like this. So this is what we were particularly looking for, but you probably saw this science report recently about phosphine being detected in the alleged detection of phosphine in the atmosphere of Venus. And Frank Drake has talked about this too. He says, life could be found in a number of different places that seem inhospitable to us. I mean, you look at some of the unique life on this planet, with discovery of microbes that exist in hostile environments, down to the depths of the ocean, or extremely frigid areas on Earth, or even when you go to Yellowstone National Park, and we find microbes living in sulfuric pools there on that particular area. So it becomes an interesting question of what constitutes life. Elizabeth Blackburn, who is a Nobel Prize winner in medicine, whose work, it focuses on life extension for humans, and she's looking at what causes aging. And I ran into her a few years ago at a conference, and she wanted to talk to me about Kepler. And she says, she was keenly interested in it because she says, don't you think it'd be interesting if we found something out there that is not carbon-based? I said, like what? Like silicon or boron. And because they're high on the periodic table. And I said, yeah, but carbon combines so easily with the other elements within our periodic table. And I said, more likely it would be carbon-based. But I said, I don't rule out the possibility that life is developed differently elsewhere in the galaxy. But it gives us, the Kepler mission gives us an appreciation for something that we are familiar with, because I think in many scientists, they start with what's familiar as they proceed into the unknown. I think as we conduct more scientific missions in the future, I think we're going to find more surprises that are before us. So I know that's sort of a roundabout way of trying to answer the question, because that's $1 million question. Mm-hmm. I'll end there with that.
Yeah, fair enough. Yeah, okay, thank you. How do scientists choose location for where to collect samples from a particular asteroid or comet? Is it chosen before launch, or is it live mapping done by, say, spacecraft to choose a sample collection spot?
Oh.
Or you just use a magic hat or something and throw and see, oh yeah, this is where we'll go.
Oh. In this case, Jezreel Crater was picked years ago, and they always wanted to go there because of the evidence that a lake existed there in Mars's geological past. Now, how do they pick it after they've landed? They have several instruments on board, and I think they're going to be doing some survey as they're going to move slowly through that crater. And I would defer that question to some of the PIs, because I'm not a geologist, I'm not a biologist, and so I would defer to them to answer the preciseness of that. But I think if you do some digging into the Perseverance mission and you look at the science behind it, particularly when you start looking at those, why did they pick even 43? Why 42 or 44? It's like, why 43? You get these tubes. They're going to sample various parts in that crater, but I don't know what the decision criteria that are using on why they pick this particular area to take one of those 43 tubes and collect from that specific area. There has to be a reason for it, because I don't think they flip a coin and just say, we'll do here. There's a science behind it. NASA, when you talk to these principal investigators, and they're just brilliant people, they have a rationale on why they do a certain thing. Very few times we just toss a coin in the air and just say, we'll see where it lands. There is a rationale behind it, and I know that's that may not be the best question for the best answer for the questioner, but I would recommend that if they're keen about that particular area, I would go check out that Perseverance website.
Okay, thank you. Next one is a bit interesting. Do you have any advice for people looking to move into the space sector, especially after a long career in other areas?
Well, follow your passion for one.
Yeah, that's true.
I was on a university campus recently, even during the pandemic, and everybody, of course, was reminding of social distancing. Everybody's wearing masks, and this university, and Paulus, you heard me talking about this earlier before we started the live session.
Yeah.
And we were celebrating this university's first satellite because NASA had started an education and public outreach program several years ago with universities in all 50 of our states. And we would basically give them a grant, you build a spacecraft, we will launch it, you operate it, and you learn a little bit of engineering from that. And you also learn about what it's like to participate in spacecraft engineering or space operations. So I had an ulterior motive when I was there, though. You look at NASA, and you look at the average age of the NASA workforce that took us to the moon back in the 60s, and that average age was just 28. That average age of the NASA workforce is a bit north of that now. And it's largely because there's you look at how the information industry and other things have developed around us, from Facebook and Twitter and all these other things. Everybody has an interest. And so we are still wanting to attract the best within NASA and also with the European Space Agency. But we've also recognized that our average age of our workforce is marched up a little bit. And so we're wanting to attract a younger generation into NASA. So it depends upon what your interests are. If you want to be into exploring in science, this is a place. And that's one of the things we sell to these young engineers that want to come work with us. Some people get off on designing the next iPhone. Well, how would you like to work with us on developing the life detection that we would use for Enceladus to prove that there's life in that ocean that's underneath the ice that covers that moon? So some people would rather do one or the other. It depends on what your preferences are.
Yeah, follow your passion, isn't it? As you said at the start.
Yes.
That's perhaps, yeah. Okay, we'll take on one last question, perhaps. Is there any plan from NASA for the next mission to Proxima Centauri B or other exoplanets?
Well, you probably heard about the Breakthrough Foundation. There's a former NASA Center director who's running that for Yuri Milner that's funded by a consortium of a few billionaires. Because maybe it's largely a result from the Kepler mission and the confirmation or affirmation that Earth-sized planets and habitable zone are plentiful, and there is an alleged detection of an Earth-sized planet in that star system. It's it's our closest stellar neighbor. And so Breakthrough Foundation has an idea of sending these little, I call them Starship Enterprise, little chip-sized things in which they would throw thousands of these things up there and they'd blast them with this laser energy to try to accelerate them to sub-light speed so that they can do a flyby of that planet and take pictures and then send those back to Earth. And I said, well, even if you're able to do that, accelerate those things at sub-light speed, you're looking at, a 25-year mission to make that happen. And so NASA right now, we do not specifically have a mission that's designated to go that, even though the Breakthrough Foundation has talked with us several times, and we've supported some of the brainstorming sessions about the technology obstacles that must be overcome to do that. But I think what you're going to be seeing from NASA is a further extension of our reach into the planetary system again, because as you know, we have had 5 missions that are now on their way to the stars, even though they were meant to be planetary exploration missions. Voyager 1, Voyager 2, Pioneer 10, Pioneer 11, and now New Horizons. All those missions were meant to explore our solar system, but they've now either have left or are about to leave the solar system, and thousands of years from now, they will pass by a nearby star. But there's some fundamental research into propulsion systems that are just science fiction dreams today that we would have to accomplish to allow us to become an interstellar traveling species.
Right. Yeah, that's true. Okay. I think we'll close our Q&A there. Perhaps bit of an appreciation from my side, Roger. I think I'm very impressed with the lecture you've shared and the knowledge you've shared with us, especially some of the keywords. I'm not trying to summarize because I think you ended up the lecture in a very high note with the right level of summarization of the entire presentation. But some of the key notes for me to take off is planets are everywhere around us, wherever you looked, and planets are far outnumbered the stars. I thought all I can see is stars right now, but I never thought there are so many other planets around. So that's a bit of eye opener for me. So yeah, there are quite few useful information you've shared, and gave a glimpse of what next to look into from NASA as such in the space. So yeah, that's very helpful. So I would just like to thank your efforts and your interest to share us and come back and give us a lecture. That's really phenomenal. And a personal thanks as well. You've been very kind, offered a few different times to trial the Microsoft Teams. Obviously, at the start, it did not go well, as with any other technology and systems. But we were there eventually. So yeah, it's all worked and come together good, really. So that's I really appreciate that, and I appreciate you gave us an extra effort and extra time for us to trial this a bit. So which is really helpful, I think. So thanks a lot for your time and giving us this lecture today, Roger.
It's been my pleasure. Thank you for inviting me.
Yeah, if we had this as a face-to-face, I'm sure all our participants would have joined us and clapped their hands. So I'm doing on all their behalf. Thanks a lot. And yeah, just one thing before we close off. So let me share. I just wanted to end up with a view of sharing a notice. So next week, not next week. So we have our next lecture, which is planned for 11th of November, 4th of November. Sorry, it's Wednesday, and it's going to be by Mandy Hickson. She is, I think, she's fairly familiar, and she's a very positive speaker. So it will be a very good lecture, I think. It's a joint lecture between IMechE, IET, and Royal Aero Society. Watch the space for future comms on this, how to register. So I'll be sending out the poster fairly soon. With that note, I'll draw the lecture to close today. Thank you, everyone. And once again, thank you, Roger, for joining us.
Thank you.
Have a good day.